Hey, welcome to Electros Classroom series. I am Daniyal Qureshi, and today, my dear friends, we are going to see capacitors and inductors in AC circuits when they are energized by an AC source. I must say that this is one of the most complicated topics to understand properly. I have seen students who just know how to use the formulas, but they really don't understand how it works. But you don't need to worry, I am here and I will try my best in order to make you understand this topic. This video is sponsored by EH Animation, which is, by the way, my own firm. More about it later. But before we start, it is very important that you first watch my previous video, because in that video we have already covered capacitors and inductors in depth. So right now, go there, watch the video completely and then continue from here. Okay, just to recall, in the last lecture we saw capacitors and inductors specifically in DC circuits. Okay, when they are energized by a DC source, what exact behavior do we get? Okay, but here now that source is replaced by AC source. Okay, now AC source is actually a source which alternates between a maxima and minima. Okay, and the maxima is actually a positive cycle and the minima in the negative cycle, or the value is actually negative. Okay, and it oscillates around a central value. Okay, that is 0. Okay, so now let's consider. We'll directly jump to the waveforms because the working we have already covered in the previous video. Okay, so now an AC source is mostly actually a voltage source, an AC voltage source. Okay, and if you don't know, you can already check my video on voltage and current sources, but mostly it is an AC voltage source. Its waveform is something like this. Okay, it is mostly a sinusoidal wave. So it is actually a voltage. Okay, the current can be anything, but the voltage will not change. Even if you apply anything, the voltage will not change. Okay, it will remain constant. Okay, it will remain constant. Actually, it will vary, but at a certain point. Okay, at a certain point, like here, it will not change. Okay, so this is the voltage waveform. This continues and it will go to its Vmax, and here minus Vmax. Okay, that's same, and this is 0. So in the case of capacitors, let's see first. Okay, in the case of capacitors, so what will be the current profile in the case of capacitor? What current profile will be there? Will it be in phase with the voltage? No, actually, you know, this is the current waveform. Okay, this is the current wave that I am drawing, which flows through the capacitor if you provide such sinusoidal wave. Okay, or an AC wave. So in the case of capacitor, you can see that the current actually starts first. Okay, this is the current wave. Okay, let's consider here. Okay, so the current actually starts first than the voltage, and this is because the capacitor charging current is instantaneous, almost instantaneous. Okay, it charges rapidly rather than, you know, the change in voltage. Okay, the voltage across its terminal actually changes very slowly. Okay, it actually takes time to build up. Okay, so that's why this voltage waveform is lagged. The voltage actually lags in capacitor by a certain angle, and same is the case with inductor. If you see, same is the case with inductor, but there is just a reversal of condition. Okay, just reversal of condition. This is the time axis and this is 0, that is Vmax. Okay, I'm again drawing this. This is the voltage waveform that we are providing by the source, and this is actually for inductor. Okay, so what is a current profile of inductor when you provide this? It is something like this. You continue this to this side. Okay, now here you can see that the current lags the voltage by a certain angle. Okay, and why? Because by the very fundamental property of inductor, we already know that it resists the change in current. It doesn't want any change in current. Okay, so the voltage actually builds up first across the inductor rather than the current flowing through it. Okay, so it actually tries its best to minimize the change in current. Okay, so that's why the current waveform is delayed by a certain angle. Okay, or by a certain distance, by a certain phase. Okay, and it is also said that this phase difference between voltage and current in inductor and capacitor is actually 90 degrees. If you know, this phase difference is actually 90 degrees. And even here you can observe, this is the 0 position. Okay, this difference is actually pi by 2, that is 90 degrees. And why this is so? In the case of capacitors, the voltage lags the current by 90 degrees Okay, this is actually 90, and here current lags voltage by 90 degrees. Okay, if they are pure and ideal inductors and capacitors. Its explanation is very simple. It is actually in its fundamental charging and discharging curves itself. Okay, so simply go and watch the previous video. You'll yourself get to know this basic concept. And another thing to remember is that this phase difference is independent of the value of inductor or capacitor. Okay, its inductance or capacitance value does not affect the phase difference, but these values do affect something else. And if you see, they actually affect current and voltage values. They actually suppress that difference. Okay, they actually suppress their values. Okay, like here in the case of capacitor, if the value of capacitance is higher, it will actually suppress the voltage. Okay, and here inductor, if you increase the value of inductance, it will actually suppress the current. Okay, because inductance is large, it will oppose that current largely, okay, to a large extent. Okay, but this phase difference will not change, and same is the case with capacitor. Let's move forward. Now these elements, capacitors and inductors, are frequency dependent elements, and by frequency dependent I mean that there is a quantity which changes. There is a quantity which changes according to the frequency, and that quantity is actually their reactances, their respective reactances. And their reactances are denoted by XC, that is capacitive reactance provided by capacitor, and XL, that is reactance provided by inductor. Now what exactly is reactance? Reactance is actually the opposition to the flow of current which are provided by these reactive elements, which are inductor and capacitor. Okay, very much similar to that of resistance. But here in AC circuits, reactances are imparted by these reactive elements, okay, by capacitors and inductors. And impedance is actually a combination of reactance plus resistance, okay. But here we are actually only focusing on reactance, okay. Now, reactance is actually a frequency dependent quantity. Now, omega is actually the angular frequency. Angular frequency omega equal to 2 pi f, okay. So here, from here you can see that the capacitive reactance is inversely proportional to the frequency, whereas the inductive reactance is directly proportional to the frequency. Okay, in the place of omega you can directly replace 2 pi f. Okay, and f is actually the frequency which you are providing, the frequency of signal or the frequency of source that you are applying to the inductor. Now here, if this is inversely proportional, this is directly proportional. So in the case of inductor, you can see that the inductive reactance, variation of inductive reactance with respect to frequency, its curve will look something like this. Okay, very much linear, definitely from here omega L. Okay, this is very linear equation where L is the constant, and also in omega we have 2 pi f. So 2 pi is also constant, and f is the only variable. Okay, so it will be linear. Earlier I thought, and I'll rectify my mistake, that in earlier videos I have shown XL as small curve. Okay, I have actually shown it as an exponential curve, but it is actually a straight curve. Okay, do remember. But here in the case of capacitive reactance, this is actually, you know, somewhat like exponential decay, because it is actually inverse. Okay, and if you even mathematically calculate, this is actually correct. Okay, it will go something like an exponential decay. So from this, what we can conclude? First, for capacitor, let's see at lower frequencies. Okay, frequencies closer to zero. Frequencies closer to zero, it actually means that we are providing a DC signal, more DC characteristics. Okay, closer to zero. So closer to zero, if you provide DC or very low frequency signal to capacitor, it will provide a very high reactance, very high opposition. Definitely, this is very much logical. If you are providing DC to a capacitor directly, so it will act as an open circuit after stable condition. Okay, once the capacitor is fully charged, it will act as an open circuit. Okay, because definitely it is just a separation between two plates. And then after that, if you further increase the frequency, it will slowly decrease its reactance. Okay, capacitive reactance, until at a certain point it will almost approach to zero. So at higher frequencies, capacitors actually behave as short circuit. Okay, they will provide very least amount of reactance at high frequencies. But in the case of inductor, it is opposite. Okay, for lower frequencies very low, or you can say that when we provide DC to the inductor, okay, DC, definitely inductor is essentially just a piece of conductor. So if you provide DC to that, it will directly, at stable condition, it will act as a short circuit. Okay, it will not provide any reactance. But if you increase the frequency, it will gradually increase its reactance. Okay, which it is a very much linear curve. So at high frequencies, it will act as an open circuit. Definitely, if the frequency is very much higher, it doesn't want any change in the current, so it will increase its inductive reactance. Now, to better understand the theory, let's go through some circuit simulations in which we'll simulate some capacitor and inductor circuits. Okay, so I have opened the fullstack.com online circuit simulator. It's a really good online circuit simulator which you can use to visualize your circuits. Okay, so first we'll see the series RC network, okay, which is energized by an AC source. You can see here, and you can also see the current oscillating. Okay, these yellow dots actually represent the current oscillating, and it is actually going back and forth due to this AC voltage source. Okay, first of all, this resistance value I have set it to a very lower value, that is only 1 ohms, and here the capacitor is 400 microfarads. Okay, and at the bottom you can notice these 3 graphs having a couple of waveforms, 2 waveforms, and the green waveform represents the voltage and yellow is for the current waveform. Okay, so the first one is for the AC source, this first block, second block is for the resistor, and third is actually for capacitor. Okay, now first let's look at the waveforms of the resistor. Okay, so you'll notice that the voltage and current waveforms in the resistor are actually in phase. Okay, and this is because you can see that the maximas and minimas of both the waveforms are actually at the same instance in time, and this is actually the inherent property of resistor, that the current and voltage across it actually remains in phase. Okay, but at the capacitor side you can see that the current, okay, let me stop it first. Okay, we'll stop the simulation in order to have a better look. Okay, so see the current waveform, it actually attains its maxima of around 360 milliamperes when the voltage waveform is almost 0. Okay, so we can say that there is a 90-degree phase shift between these two waves. Okay, and it means that the current waveform is 90-degree ahead of the voltage waveform. Okay, and this is exactly what a capacitor does in a circuit. You will also notice that in the AC source, you'll see that these two graphs are almost the same. Okay, here also the current waveform is is achieving its maximum when the current is almost 0. Okay, and why this is so? This actually represents the current that is overall in the circuit. This is actually the series current. This is actually the current provided by this AC source. Okay, so why these both graphs are same? This is because due to the overall nature of our load which we have connected. Okay, just see that here our overall load is actually capacitive, because the capacitance actually dominates here in the circuit. Okay, this capacitor actually dominates the load in the circuit, and that's why you will see more capacitive effects at the AC source side. Okay, or a more capacitive load will be experienced by the AC source itself. Okay, but notice while we change the value of resistance, what will happen? Okay, I'll start the circuit. Okay, and now we will increase the resistance value. Okay, so I have increased the resistance value, and now let's see what happens. Okay, it will take a while to auto zoom, and now yes, it has done. So notice that now both the waveforms are in phase. Okay, the current and voltage are now in phase. So how this is so? Okay, why? This is simply because we have increased the resistance dominance in the circuit. Okay, now the load is said to be more resistive than capacitive. Okay, the capacitance is also there, but it has very less effect as compared to the resistance. Okay, so it is all about the overall load that you have. What is its nature will be affected and will be reflected actually in the source itself. Okay, now let's change the capacitance to see its effect in the circuit. For this particular value, you can see this much amount of current is flowing, and at its peak it is around 200 milliamps. Okay, now I'll increase the capacitance. Okay, like till here, you'll immediately notice that the current actually is higher. Okay, the current is higher, and we can also verify it is actually 250 milliamps at its peak, and the voltage is actually suppressed. This is exactly the nature of capacitor. Okay, capacitor actually tries to suppress the voltage, but if the capacitance value is much higher, a higher capacitive effect will be experienced, and it means that a higher current, a higher instantaneous current, a higher charging current will flow. And definitely you can see that the current is increased while we increase the value of capacitance. Lower the capacitance, lower the capacitive effect, so lower the charging or discharging current will be. But here we have increased the value, and that's why we are experiencing a very high current in the circuit. Okay, and the second thing to notice is that irrespective of the value of capacitor, as already we have stated, the phase difference will not change at all. only the values, the magnitudes of these waves will definitely change, but not the phase difference. Still the phase difference is actually 90 degrees. You can see that from here, okay. And lastly, let's see the effect of frequency on the circuit. Okay, so at this particular frequency of 28.8 hertz, you can see that this much current is flowing. Now what will happen when I'll increase this frequency? Okay, slowly I'm increasing, and you will see that the current is also swinging back and forth fastly, and that means that a higher current is actually flowing through the circuit. And why this is so? This actually fits perfectly with our theory that we have studied just now. Okay, that capacitor at higher frequencies behaves more like a short circuit. Okay, so at a very high frequency, you'll see that the current is much higher than the voltage. Okay, earlier at lower frequencies, what you see that the current is lower, okay, and the voltage is higher. But at higher frequencies, a very high current actually flows, so much so high that it also surpasses the voltage waveform itself. Okay, so another point to note is that the resistor, irrespective of the frequency provided to it, okay, irrespective of the number of components and their values connected to, but the resistor will always be in phase. The resistor's current and voltage will always be in phase, okay, because resistor is actually frequency independent element. It is the most basic element, so that's why resistors are very ideal to measure circuit parameters. Okay, so what you do is simply connect a small resistance in parallel or series in the circuit in order to measure the parameters specifically in AC circuits. Coming to the series RL network, where we have these three elements connected in series, and these three scopes connected to the individual elements. Now again the resistor be like कि मुझे कोई फर्क नहीं पड़ता और बेचारा सफर करता है ये AC सोर्स, ये इंडक्टर और कैपेसिटर की वजह से जो सर्किट में लगे हुए हैं. ओके, हाँ, so again the phase difference between the voltage and current waveforms in the resistor will be zero, but here in the inductor you will notice that the voltage waveform is actually leading by 90 degrees to the current. This is exactly what we expect from an inductor, as we have already seen. Okay, and the same thing here, the resistor value is very less, that is 1 ohms. Okay, so this value is very negligible, so this load will be more inductive, and that's why we'll see this same graph over here at the AC source. You can see that the voltage is leading the current, okay, definitely. And if you increase the value of resistance, you can see that I'm increasing. Okay, so again by increasing the value of resistance, we are actually making the overall load to be more resistive in nature, and that's why these two waves are again in phase. And if we decrease, then you'll get the phase shift due to the inductor. Okay, this circuit will be more inductive. Now let's change the inductance and see its effect on the circuit. Okay, so if I increase the inductance, you will see that a very low current is flowing through the circuit. And why this is so? Because you are increasing the inductance effect. Okay, so what it will do, a higher inductive effect will suppress the current more. Okay, it will suppress the current more, definitely, and that's why a lower current will flow through the circuit. Like at high, you can see that around 65 milliampere is flowing, and if we reduce the inductance, a higher current of 260 milliampere is flowing. Okay, because the inductive effect is now being lowered. Okay, but even at lower values of inductance, you can see that a higher current is flowing, definitely, because the inductance effect is now reduced, and so a very high current will flow. Okay, like something like 450 milliamperes. Okay, and finally let's see the effect of frequency on the circuit, how it behaves. Okay, so at a particular frequency of 23.8 hertz, you can see this much amount of current is flowing through the circuit. Now when I'll increase the frequency, what will happen? Okay, now let's slowly increase the frequency. So as I am increasing the frequency, you can see that a very lower current is flowing. You can see here. Okay, the current has reduced drastically. And why this is so? Because due to the property of inductance or inductive reactance, okay, at higher frequencies, this inductor will impart a higher inductive reactance on the circuit. Okay, so it will oppose the current highly as compared to at lower frequencies. Okay, so that's why we are getting a lower current. And at very lower frequencies, okay, if we increase the frequency like at 4 hertz, you can see that at lower frequencies it will allow maximum current to flow through it, because now the inductive reactance is very less. Okay, because it is directly proportional to the frequency. So lower the frequency, lower will be the inductive reactance, lower will be the opposition which is given to the current in a circuit. So from this we can conclude that a capacitor and inductor, if they are ideal, okay, if they are the only element connected in the circuit, okay, they will produce a 90-degree phase shift. Okay, if they are pure elements. If they are not pure elements, definitely in the real world they will have some parasitic resistance, parasitic inductance. Even a capacitor has some parasitic inductance in it. Even an inductor has some parasitic capacitance in it. Okay, so due to these elements, the phase shift will not be perfectly 90 degrees. Okay, there will be they will definitely be lesser than 90 degrees, because the phase shift cannot be greater than 90 degrees. Okay, do remember that phase shift in any AC circuit cannot be more than 90 degrees. Okay, so in real world the value will be more like 89.99999 something. Okay, or if you are connecting something in series with the element, okay, like a resistor or inductor, then it will be anything between 0 to 90 degrees. Okay, now time for our sponsor. EH Animation provides premium 3D animation service mainly to businesses. It's a B2B service. So if you own a business and want to grow it, it's worth checking it out. I have provided the links in the description below. And that's it for today, guys. Hope you enjoyed the lecture, and if you did, then please like, share and subscribe. Comment down below if you have any query or any suggestion. Thanks for watching and see you there.